Hi students, welcome back to geology. Today we are talking about sedimentary structures and sedimentary rock identification. So first step is looking at bedding. So when sedimentary rocks are deposited, they are deposited in a horizontal fashion. And that horizontal fashion, when it's compressed and solidified into a rock, presents bedding. And bedding is layers of sedimentary rock that has compressed and formed over thousands to millions of years. And so, depending on the thickness of each bed, you can look at how much material was deposited at a particular time. So, maybe there was more material deposited, giving you thicker beds. There's thinner beds, there was less material, or maybe there was less time of material accumulating before the rock solidified. And so the sedimentary beds, which we also call strata, can tell us an indication of what was happening at the time of deposition. But generally, these beds are going to be found to be horizontal unless something has happened to them like tectonics or faulting or folding. So with rocks, we're usually looking at formations. And so the formations are just distinct rock units that tell us something about the rock features. So these are either particular rock types, particular rock ages, and those create a formation. And so we kind of group the rocks together, and these ones show you the different beds as they go up, and those different beds are separated by the different rock types. A random person might just look at these rocks and be like, oh, it's just rocks. But there's lots of different rocks within here. You have some shales, we have some sandstones, we have some limestones. And so the beds separate those rock types in addition to those formations. We can also see ripple marks preserved in the rock. And ripple marks are from some sort of erosion of either water or wind. And depending on the direction of the wind or the water, whether it oscillates back and forth or it's a one direction, you're going to get asymmetrical or symmetrical ripples in your sediment. With symmetrical ripples, we're looking at something that oscillates back and forth. So this might be at like a beach. So these are waves that would oscillate back and forth. And so your slopes are equal on either side of those ripples. With an asymmetrical ripple, we're looking at one slope that is gentle and one slope that is steep. And so you get an asymmetrical look to your ripple marks. And this can happen with one direction of ripple. So what happens here in like a dune setting is wind picks up particles, and those particles then get deposited on the other side of the slope. And eventually it just starts to create this larger asymmetrical ripple that you can see in the upper left-hand corner there. And that asymmetrical ripple will eventually form into a solid rock if it ever gets lithified. And so dunes are a really good example of where we would see an asymmetrical ripple, because for a significant amount of time, we see wind going in one direction. And then when the wind changes direction, we see a whole different shift of this material to the other side, to the other direction. We can also see mud cracks preserved in rocks. And so the mud cracks here can either come as a cast or a mold. So if you've ever noticed when it rains and then we have a hotter day after a rain, you'll start to see water evaporate really quickly. And when that happens, the material starts to crack and contract as it dries, and that leads to the mud crack. And if that mud crack gets filled in with sediment on top, and then that gets preserved into a rock and removed, we call that a cast. And so on a cast, the ridges that you see there would have filled in the original mud crack. And so it's actually just preserving the mud crack on it, but it's not necessarily the original crack. The mold would be the original mud crack. And so a cast will have these raised ridges, and these raised ridges would tell you that that material is pointing the other direction. So you'd have to turn the rock around and say, okay, so the ridges pointing down would be the correct original orientation of this sediment. And so all of this is just telling you about the past environment of the rocks in the region that you're looking at. We also see cross-bedding in sedimentary rocks. With cross-bedding, it's similar to the dune formation, where it's starting to form the ripple marks. But over time, if these large-scale features get stacked up and preserved, we get what we call crossed beds or cross bedding. And so what happens is material is picked up on the wayward side of the dune and then is dropped down steeply on the other side. And eventually, as those materials get stacked up and solidified or lithified into a rock, it creates kind of this wave to the bed. Instead of it being horizontal, we see kind of this curve feature. And if this occurs over time and we see the stack up of this, it'll get preserved as cross beds in a rock and not just sediment stacked up this way. So this kind of shows you that progress of cross bedding occurring where wind is pushing one direction and material is stacking up on that steeper slope side. Eventually you get large formations like this, or maybe microscopic ones like some that I found kind of east of I-5 near Firebaugh-ish, where I have these little microscopic little cross beds, or they can be really large scale like some of these other photos. But you see kind of that wave or that curve, and that is no longer horizontal beds. We're looking at crossed beds, which is why they're called cross bedding. In a marine environment, oftentimes a continental shelf might fail in a submarine landslide. And if that occurs, all of that sediment that comes down gets thrown up into the water column. And we get something called graded bedding, where material in that, what we call turbidity current, settled out by grain size. And so because water has a higher density than air, the material, some of it is closer to the same density as water, and so it'll sit in the water column longer, but the heavy material is going to fall out quicker. So things like gravel are going to settle first, and then you'll see sand, silt, and then clay. And so there's this gradation to the bedding as you go from the bottom of the material up. And so that also gives you an indication of which direction was up in a sedimentary environment when these rocks were deposited. And so here, this guy is pointing to a couple of series of different turbidity currents that happened over time, creating graded bedding in a few different layers. And so you look at a rock and say, okay, I know which direction is up based on the grain size. So on that upper right-hand corner there, the grain size is largest at the bottom and it's finer at the top, which means that it is oriented in the right direction that it was deposited. If it was upside down, we would say that it was upside down because the graded bedding tells us that the largest particles should be at the bottom. So here's a look at those turbidites, the turbidite current. So you can see the submarine landslide coming down there. All the material is thrown up into the water column. And then as the material is settling, it's settling by its density. And then the resulting is the graded bedding where largest particles on the top and it finds upward. All right, so sedimentary rocks are really unique in that they are the only rock type that is going to contain fossils. Why do you think that is? Why would sedimentary rocks be the only rock type to contain fossils? Well, with igneous rocks, they are created from molten rock, which is going to melt bones and other organic material. And metamorphic rocks are formed from intense heat and pressure. So intense heat and pressure puts a lot of intensity on bones and other organic material, and they are going to basically disintegrate. So you're not going to see them preserved in those rocks. You're going to see them preserved in sedimentary rocks because they're a lot more gentle as far as the making of a rock is concerned. And so we would often see fossils in these rocks, and these fossils will tell us something about the depositional environment as well. So if we see corals and echinoderms and things like that in these rocks, then we know that we're looking at saltwater depositional environment. That's where these rocks formed. If we see insects or amphibians, we might be looking at freshwater, so maybe lakes or rivers. And then if we see leaves and land animals, they would be terrestrial, which means they formed on land. So if you have a rock that contains T-Rex bones in it, you know we're looking at something that is terrestrial or formed on land. The color and chemistry tell us something about the environment in which it formed as well. So if we see red beds like this image here, we know that that's going to be terrestrial because we need the oxidation to occur at the surface, right? We need exposure to oxygen in order for those iron minerals to start to rust. Okay, and then we have black shale. If we see a really, really dark colored shale, we're looking at an oxygen poor environment where there wasn't a lot of development of color. And so this is probably going to be something that is really, really deep water. And then in evaporites like halite or rock salt, those are going to occur in arid environments or arid climates where there was water present and it evaporated quickly, and so salt content was left behind, forming these evaporites or forming this rock salt. Okay, now we are looking at classification of sedimentary rocks. So the two basic ways that we classify sedimentary rocks is by their type and their composition. Okay, so first thing is type. So with type, we have clastic sedimentary rocks and we have biochemical sedimentary rocks. So with clastic sedimentary rocks, these are made up of sediment. They're made up of fragmented material, and they can either be deposited by water, wind, glacial activity, or gravity. Okay, and with biochemical sedimentary rocks, we are looking at something that formed from either evaporation, precipitation, or biogenic sediments. And so they could have a chemical component or they can have a biological component, but they're not necessarily made up of just sediment or fragmented material. And then within each of those, we can look at the composition of the sedimentary rock. So we can look at either the grain size with our clastics, we can look at the chemical or mineralogical makeup of our biochemical, or we can look at the biological makeup of the biochemical. Okay, so starting with the clastic sedimentary rocks, we have the different sediment sizes, which we've already talked about in the last lecture. There's gravel, sand, silt, and clay. Gravel is your largest particle. We're looking at 1 millimeter or larger. Sand is 0.01 to 1 millimeter. Silt is 0.001 to 0.1 millimeter. And then clay is less than 0.001 millimeter in size. Okay, and then the rock type is listed there for you as well. Gravel is going to create conglomerates or breccias. Sand is going to create sandstone. Silt is going to create siltstone, and clay is going to create shale. So when you're looking at the sediment size, it's really easy to identify the rock type if you can identify the sediment size with clastic sedimentary rocks. So here we have the example of the detrital and clastic sedimentary rocks. It's just the same. It's the same word, just it's the same meaning, different word. On the left there, we're looking at the clastic sedimentary rocks. And unfortunately, the sediment name on this says that mud is for siltstone and shale, but that's not exactly correct. This is from a textbook, so just keep that in mind. Siltstone will be made from silt, and shale is made from clay, not necessarily just mud. Mud is a very generic term. It doesn't really describe the sediment size exactly. They do have the sediment size listed there, but just keep that in mind. So with gravel, we have the two different rock types. We have conglomerate and we have breccia. With conglomerate, we're looking at rounded particles. With breccia, we're looking at angular particles. That's the big difference there, is the size, the rounding of the particles. Not necessarily the size. They're both the same size. With sand, we just have sandstone. I'll show you a couple of special sandstones that you might encounter. And then, like I said, with siltstone and shale, as long as you can identify whether it's silt or it's clay, you should be able to identify the actual rock name. With the chemical sedimentary rocks or the biochemical sedimentary rocks, the big difference here, the big separator, is whether it contains calcite or it doesn't. So you'll see that big box there. It says calcite, CaCO3, which is calcium carbonate, and then there's a bunch of rocks listed for it over on the right. So with calcite, it's a base, right? So calcium carbonate is a base, and it will react with hydrochloric acid. So identifying these rocks, all you have to do is start with putting a little bit of acid on the specimen. If it reacts, we know that it has calcium carbonate in it, and we can start to identify from there using the texture terms that are listed and decide which rock we're looking at. If it doesn't react, then we have to decide if we think it has quartz, gypsum, halite, or altered plant fragments in it. Okay, with quartz is going to scratch glass, so that might be a good indicator for you. Gypsum will not. Gypsum's really frail, so that one would not scratch glass. Halite is going to be salty, so if you want to lick the specimen you're looking at, but know that lots of people have probably touched it before. I don't necessarily recommend it. But it will also form these really nice cubes because halite forms in these cubes and breaks off into cubes from its cleavage planes, right? So that would give you a good indication that you're looking at rock salt. And then altered plant fragments are organic material that has compressed and formed into a rock. And so this is creating what we call bituminous coal or bituminous coal, however you want to pronounce it. And it's a very, very dark color. It's very, very compressed, and it's very, very light. So if you see something that looks that in that description, then that's what you are looking at. That one's pretty kind of oddball. It's easy to identify. Within your calcites, though, the big thing is going to be whether you can see the shells, if the shells are large, or if they're fine. So with coquina, you have shells that you can see, and they are very loosely compacted. With fossiliferous limestone, you have shells you can see, but they're well cemented together. And then chalk is microscopic shells and clay, and so it's very powdery. And the difference between crystalline limestone and travertine, these are both crystalline versions of that calcium carbonate, but travertine is layered and crystalline limestone is not. So it's a good kind of decision making for you. So with that being said, you can take a second to try to figure out which of these rocks have grains, fossils, look crystalline, whether they're clastic or chemical, and you can pause the video and make some observations. And then in lab, you will also work with these rocks to try to identify them. Okay, so like travertine, for example, there we just learned is layered, so you can kind of see the layering there. It's also crystalline, so it would contain like crystalline calcium carbonate in it, and it would be a chemical sedimentary rock. Whereas down here at the bottom, we have our classic sedimentary rocks. So those are going to be clastic. Your sandstone is going to contain sand. You can see the breccia with the angular grains there. You can see the conglomerate with the rounded particles. And then shale and sandstone are really fine particles. Shale and siltstone, are really fine particles. And you'll get to see those in lab as well. A couple of special sandstones that we look at are Arkose and Greywacke. Arkose is a very feldspar-rich sandstone, and so this one has like a pinkish, reddish color to it. It's not from red beds, it's from the feldspars being pink, and as they weathered, they remained that color. They don't change color necessarily unless they fully weather to clay. And then the Greywacke is a very angular sandstone. Sandstone's typically rounded sand grains, but in this case, in a Greywacke, it's obviously gray, and it also has very angular grains in it. So we call it an immature sandstone because it hasn't fully matured to the full round sand. So in summary for this lecture, we're looking at sedimentary structures that have preserved past environments in our sedimentary rocks and can tell us something about geologic past. Clastic sedimentary rocks are made up of sediments. Biochemical sedimentary rocks are made up of minerals or biological components. And then sedimentary rocks in general will give us clues to the environment in which they formed. I will catch you guys in the next video. Bye.